Viewers like you make this program possible. Support your local PBS station.
The entire history of science can be summarized as a sequence of one paradigm shift after the next. And when there's a paradigm shift, there's a picture, there's an image that sets the new tone for the new vistas.
You know, the mushroom cloud, the double helix, everybody recognized them. They've kind of become icons of the 21st century. They've replaced the Christian cross almost.
Visual images are important because we are very visual organisms. We have a saying that seeing is believing.
Every image tells a story, but some are more important than others.
It's an iconic image. It's turning the universe inside out.
It really is a picture that changed the way mankind views the universe.
It integrates in a single image the widest accumulation of knowledge on the Earth available at the end of the 15th century.
Some of the greatest breakthroughs in the history of science have left traces behind, images which have become modern classics. This series tells some of these stories.
Our knowledge of the outer world is a 500-year-long journey of images, a journey which has taken us from the surface of the Earth to the edges of the universe. We begin on the 20th of July, 1969, in a place which offers an unbeatable perspective of our little corner of the cosmos.
Underneath it says, "Here men from the planet Earth first set foot upon the moon, July 1969.
The photos from Apollo 11, the expedition which put man on another celestial body for the very first time, are some of the most famous in history.
The two hemispheres of Earth.
We didn't outline what pictures we were going to take. Like the view of my footprint was not on the checklist to do that at all.
They've got the flag up now, and you can see the stars and stripes on the lunar.
These images gave us a new perspective of Earth and of our own existence.
What we brought back were images of our world in ways we'd never seen or discovered before.
I was walking in this direction, and then he said, "Hold it, Buzz. Turn around and look at the camera."
Of the first two people on the moon, one is still around to tell us what happened in the summer of 1969.
Well, over in that building, Rockwell assembled a command module. It didn't look like exactly like that. It was a little bit more flyable.
After a 72-hour trip, Apollo 11 settled into orbit around the moon.
Now, everybody was nervous. A lot of people on the ground were sleeping probably as badly or as the astronauts. They were so excited. They locked the doors to mission control so that no one could come in and out during the actual landing attempt.
60 seconds.
We were still about 300 feet above the ground. And I was beginning to get a little concerned that we only had 60 seconds to get it on the ground. There was a crater with a number of boulders around it. So the easiest thing to do is to just, you'll fly over it. Takes more time and takes more fuel. And we had a light that came on, a low-level fuel.
They probably had, when they landed on the moon, enough fuel to continue hovering for maybe 30 or 40 seconds. The legs of the lunar lander touched down. They shut off the rocket engines and let NASA know that Houston, Tranquility Base here.
The Eagle has landed.
Neil Armstrong's first words are now classics.
That's one small step for man, one giant leap for mankind.
Buzz Aldrin also commented on the landscape which lay before him.
But it was after a little bit of conversation and the word beautiful that was sent by Neil, and I thought, this really isn't beautiful. It's magnificent desolation.
Aldrin did one more thing before it was time to explore the moon's surface.
Frankly, I guess the tension, the excitement of watching Neil down there and then going down myself gave me the urge to urinate. So one of the first things I did in the first couple of minutes was to use the spacesuit urine collection bag. Then I was much more comfortable to do all the other activities.
Mr. Aldrin.
Yes.
Nice to see you.
Hi, how are you?
See how I recognized you?
You can tell by the sunglasses.
No. I met you.
Neil Armstrong and Buzz Aldrin became superstars. At the same moment, it was announced that they would be the first two people to walk on the moon.
Beautiful, just beautiful.
The blurry television images were seen live by 600 million viewers as the two astronauts moved around in the strange environment. But it was the high-resolution stills which became iconic.
Oh, yes. This picture, right. I recognize it. The images that we created just by walking around were so perfect boot prints that I felt we really needed to take a picture of it.
What we're seeing here is the first significant footprint on another world. We're seeing the shadowing, we're seeing how the dust compacts in the little crevices and such. We're finding out how thick the dust is on the moon, which we had no idea.
Very, very fine-grained as you get close to it. It's almost like a powder.
There were people that thought of a first spacecraft that would land on the moon would sink in the dust, and we'd never see the astronauts again. That's how little we knew about the moon.
So it's one of those just right on the spur of the moment decisions that's turned into a rather iconic picture.
Perhaps the image which captured this groundbreaking expedition better than any other was this one.
Buzz got the chance to hold the camera for a majority of the time. And there was only one time they actually changed the camera.
I was walking in this direction. Neil took a picture, and then he said, hold it, Buzz, turn around and look at the camera. And I turned around and looked at the camera. You can see in the visor the reflection of the rest of the lander. You can see the reflection of Neil Armstrong taking this picture, and of course the shadows.
This was regarded as the first shot of a man on another world. Seeing someone walking on a world that's totally barren, and even though you couldn't quite see the face, you knew it was a human being. Our perspectives changed because we're like, wow, we've gone someplace that no one has ever gone before, and it was another world.
I've been asked why this is such an important picture, and in jest, I say, well, I have 3 words that describe the importance of this picture. Location, location, location. Oh yeah, this is the crew of Apollo 11, Neil Armstrong, Mike Collins, and that's what I looked like in 1969, yes.
But the images from the Apollo program also garnered an unexpected significance.
The thing is that when we went to the moon, we were basically competing with the Russians. We were trying to get there ahead of them. But once we got up there and we turned our eyes out towards the horizon and saw the Earth rise, we discovered how small we are in the whole significance of the universe.
In retrospect, it's been said that the most important aspect of man's journey to the moon was that we discovered Earth. The images of our home surrounded by a cold black cosmos in many ways marks the beginning of the modern environmental movement.
This is our world. We need to take care of it because it's all we've got.
The pursuit of knowledge and the curiosity to explore our surroundings has been central to human development. Long before people went to the moon, they voyaged into the unknown.
There was a time, around 500 years ago, when humans had no idea what our planet actually looked like. Beyond the horizon lay vast, undiscovered continents. One map from 1490 is believed to have been more important than any other in expanding our knowledge of the Earth.
It integrates in a single image the widest accumulation of knowledge on the Earth available at the end of the 15th century.
The map has been described as the catalyst for European exploration of the New World.
This map is important also as an unwitting part in what must be one of the greatest confidence tricks in European history, in which the most wealthy rulers in Europe were hoodwinked into believing that they should finance an expensive voyage into the unknown.
Around 1480, a German cartographer arrived in Florence. His name was probably Heinrich Hammer, but he was given the new name of Henricus Martellus by his wealthy patrons, the Medici and Martelli families.
This is an important corner between the Medici Palace and the Martelli's palace. We don't know exactly where the workshop was, but if...
Martellus worked somewhere in this quarter, in the heart of the city, where powerful families of the time began investing in science and the arts.
Florence was one of the most sparkling places in Europe, and the richest, the Medici and the Martelli, managed to add a kind of cultural lore, and they transformed Florence into a cultural capital at the world or European level.
In the 1480s, all knowledge of world geography was still based on the 1,000-year-old maps of Ptolemy the Greek.
Ptolemy's Geography is a book showing the space of the Roman Empire at the moment of its highest expansion.
In the Medici family's possession was one of the most well-preserved copies of Ptolemy's world map. It was this map that Martellus had been assigned the task of updating. And he seems to have been more suited to the job than others.
Martellus managed to use these several pieces of information to draw a new map of the world, using different technical skills and the ability to choose from knowledge that contrasted each other.
The most important news about the outside world came from the Portuguese. They were the great seafarers of the time and were mapping the coast of Africa. The goal was to find an easterly sea route to more easily reach the riches of Asia.
The Portuguese have been going down the coast of Africa since 1415, and this is where Henricus Martellus comes in. Because though Henricus Martellus was working in Florence, he had got information about the latest discoveries of the Portuguese. The same sort of information was reaching mapmakers in Venice at about the same time, but for some reason they weren't quite so up to date.
An important discovery was made in 1488 by Bartholomew Diaz. He succeeded in rounding Africa's southern tip, the Cape of Good Hope.
He rounded the tip of Africa, demonstrating that they reached the very end of the continent. What is amazing is that in 1490, this piece of information was available here in Florence. We can follow the shape of Africa.
Sometime in 1490, Martellus draws a map which depicts the appearance of the Earth more accurately than any other map at that time.
A single image that we can consider the very image, the very imago mundi, so the representation of the world available to somebody like Columbus.
A growing band of scientists now believe that Henricus Martellus' map was not only the most accurate of that time, but that it also played a decisive role in what is perhaps the single most important expedition in world history.
There's every evidence that this is the map that persuaded Ferdinand and Isabella to finance what led to the discovery of America, which by any account has to be one of the great events of human history.
There is no remaining evidence, but it seems likely that it was Martellus' map that Christopher Columbus showed to the Spanish court.
We certainly know that the printed map was circulating in the courts of Europe. That would have been the latest sort of map that Columbus could have shown to his possible sponsors.
Although the map showed that there was an easterly sea route via the Indian Ocean to the rich countries of Asia, it also revealed a long detour in order to get there.
Here you can see South Africa really breaking out of the boundary here, which emphasizes that it really is quite a way south.
For a person like Columbus, there was more to be gained from Martellus' map.
For sure, somebody like Columbus looking at this object, at this representation, could clearly see that the distance between the two edges was very little.
It was all about how large the planet was thought to be.
He was working on the coordinate, on the figures supplied by Ptolemy, and he didn't think it was all that far. So, yes, they knew it was quite a distance from Spain to Asia, but it would still be safer and quicker for them to go westwards rather than to go eastwards.
Today we know what happened. Columbus got his financial backing. He sailed west for 10 weeks, and on the 12th of October, 1492, he made landfall. But of course, it was not Japan, China, or India he had reached. 30 years later, while crossing the gigantic ocean on the other side of the newly discovered American continents, man began to realize that the planet was much, much larger than anyone had thought. Columbus's expedition paved the way for the westward mapping of the globe. An explosion of knowledge followed, the starting point of which can be traced back to one map, created in the narrow alleyways of Florence by a young German named Henricus Martellus.
Today, it may be easy to laugh at the thinking of the time, but in the 16th century, there was really nothing to indicate that Earth wasn't the center of the universe.
They thought that all the heavenly bodies were in motion around the Earth, which is how it looks even now if you watch the planets from night to night.
Common sense says that the sun rises in the east and sets in the west because everything goes around the Earth. However, this one picture encapsulates a new worldview that violates common sense.
It's turning the universe inside out. That's what it does. It turns the universe inside out.
It was in this castle, in the Polish city of Olsztyn, that Nicholas Copernicus lived and worked during some of the most important years of his life. It is here that the great astronomer's only remaining instrument is preserved.
He was work as administrator of the Warmian chapter property. And during his stay in the castle, he made this astronomical table, the only one astronomical instrument preserved to our time.
It's a sort of calendar which Copernicus created in order to tackle one of the astronomical problems of the time.
The Julian calendar was not perfect. Date of equinox was about 11 days from the exact astronomical date. So for that reason, this table was a kind of a solution of this problem. He just put the flat mirror on the Windows ilk. In one specific day, the day of equinox, the way of the sunspots is just straight line. So in such a simple way, Copernicus was able to find the proper date of the equinox.
But Copernicus and his contemporaries faced an even greater problem. The belief was that Earth was the center of the universe. Once again, it was Ptolemy that people were turning to. His geocentric model placed Earth squarely in the middle, and around us rotated the Moon, then Mercury and Venus, and finally, the Sun. Intricate trajectories for the planets were required for the model to work.
Because the Earth and the planets really do go around the Sun, if you try to arrange everything so that they're going around the Earth, you have to do a lot of complicated motions.
Planets stopped and they moved toward the west, so there is a retrograde motion, and it was very difficult to explain what is the reason of the loops they made on the sky.
Planets which sometimes moved faster and sometimes slower, only to then change direction altogether, was something Copernicus found odd.
I think he was looking to make it more uniform. That's what he said. Copernicus believed that everything moved in a uniform way. You couldn't speed up and slow down.
It was when Copernicus tried to get a grip on the peculiarities in the Ptolemaic model that he tried a cosmic swap.
And somehow, in his thinking about the motions, he tested the idea of putting the sun at the center. And when he did that, the planets lined up in order of their speeds.
Suddenly, planetary movement across the heavens became considerably easier to understand.
So when he saw that by putting the sun at the center, you could see the rational order of the planets, that must have convinced him that he was right.
Dzień dobry. Czy mogłaby Pani użyczyć na chwilę książkę De Revolutionibus Copernica? Proszę bardzo. I'm looking for the famous diagram. It is in the first book of the Revolutionibus. And this is the picture that show the sun in the center and orbits of planets: Mercury, Venus, Earth.
Copernicus' famous book was published in 1543, but today we know that he bore this radical idea for several decades prior to this.
It seems that by around 1510, he communicated this to a few other people and told them he was writing a book. But then the book never appeared. So decades went by, and he remained silent.
Copernicus lived in a deeply religious time, and he had every reason to be cautious.
Copernicus was no fool. He realized that he could be excommunicated or tortured for presenting ideas like this.
He waited because he was frightened. Copernicus was worried that people would accuse him of a form of heresy.
Had it not been for the unexpected visit of a young German astronomer in 1539, Copernicus may well have taken heliocentrism to the grave.
His disciple was named Rheticus, and this was a young mathematics professor from Wittenberg who heard about his work and traveled to see him. Well, he wasn't expecting him. I mean, the young man just arrived, sought him out, and traveled 500 miles to find him.
Rheticus became Copernicus' pupil, and he played a decisive role in finally convincing Copernicus to publish his ideas.
He was the one who convinced Copernicus to publish, after all, and then actually took a copy of his manuscript to Nuremberg and got the book printed. By the time he had the book rolling, Copernicus had a stroke. The minute the final pages reached him, he died. So he never knew the reaction to the book.
Copernicus' heliocentrism, with the sun instead of the Earth in the center, marked the beginning of modern astronomy.
It was this picture that set into motion the Copernican revolution. After this book was published, the floodgates began to open. All of a sudden, we had a whole new generation of astronomers that were not beholden to the old picture going back to Ptolemy.
Once the theory had been accepted by astronomers, the Church was quick to react.
Well, in 1616, Galileo began speaking out in favor of Copernicus, and that's when the Church moved to censor the book.
Copernicus' heliocentrism was considered so dangerous that it was on the list of books banned by the Catholic Church until 1835.
It was the first step toward accepting that the Earth is not fundamentally different and we are a planet in space.
Renaissance astronomy and the age of exploration lay the foundation for our understanding of the Earth's appearance and its location in the solar system. But it would be several centuries before man understood anything about the planet's prehistory.
Many people had noted how remarkably well the two continents seemed to fit together. South America and Africa were like two pieces of a puzzle. An image from the beginning of the 20th century suggested a solution to the mystery, which no one thought was possible.
These are maps of the fit of the continents. Beginning about 200 million years ago, the continents rifted apart in the Atlantic, and we see opening of the Atlantic Ocean.
The image suggested that the planet had a dramatic past and that violent forces had reshaped its face. It wasn't until the 1970s that the first fully complete map of the Earth was published. A map showing the Earth's entire crust, even the parts hidden by the great oceans of the world.
So this is the Heezen and Tharp map of the global ocean floor. It was published in 1977, and it provided the first image of the predominant global features of the ocean floor as we know them now. And the largest structure on Earth was revealed in this map, and that's the mid-ocean ridge, which extends from up here in the Arctic Ocean, splits down the center of the Atlantic Ocean.
The so-called Mid-Atlantic Ridge was shown to bear the evidence for a theory that was formed almost exactly 100 years ago. The German meteorologist and geophysicist Alfred Wegener was the first to formulate a theory which correctly tackled the mystery of Africa's and South America's strange fit. Wegener examined fossils from different parts of the world and began to see a pattern.
Common species of animals were found on continents that were now very far apart, so fossils of reptiles in South America and Africa.
By marking the fossil locations on a map and joining the landmasses together, Wegener noticed that they matched each other and formed a supercontinent.
We had these fossils demonstrating that at a prior time, the same animals were found in both places. So there was strong evidence that the continents had been together in the past, that Wegener put together in his theory of continental drift.
The supercontinent was named Pangaea, and Wegener called the process by which it was broken up continental drift. But the image which described this dramatic process was not welcomed by the scientific establishment.
It was very unpopular. He presented his theories to the German Geological Society in 1912, and the key problem was that there was no mechanism for this opening of the plates that seemed viable to the community at the time.
She'd start over.
It wouldn't be until the 1950s that Wegener's ideas could be proven and explained.
I haven't been in the core lab in quite a while. How many cores do you think are in here?
6,000.
Yeah.
So we got samples from 150 million years ago to 120, 10, all the way up to 80, 60 million years.
The whole early opening of the Atlantic.
We got the whole early opening.
Here at Lamont, a part of Columbia University, drill samples from the ocean floor are preserved, the oldest dating back to the time of Pangaea's breakup, when the Atlantic Ocean began to open up.
And you were out for long, long time stretches on those ships, weren't you? Like 3 months?
3 months, 4 months, yeah.
Bill Ryan was one of those who had the arduous task of collecting the samples.
The sediment is intruded up into the pipe, and the pipes would be taken apart, put on deck.
The work was led by legendary geologists Marie Thorpe and Bruce Heezen, who made countless trips across the Atlantic in order to map the seafloor.
They had tracks of ships that were going across the Atlantic and making depth soundings beneath the ship, and they had tracks that were spaced many tens of kilometers apart.
It was from these measuring points that Marie Thorpe began to develop the first accurate map of the seafloor.
She was making profiles across the ocean floor from these soundings, and then she began to imagine the three-dimensional structures and piece together an image of what the ocean floor could look like from these very sparse soundings.
Thorpe and Heezen noticed that the seabed closest to the continents could be around 1 kilometer thick. When the boat reached the middle of the Atlantic, it thinned out dramatically.
As you went across the ocean, when you got up the mid-ocean ridge, that sediment layer would thin, eventually to a couple hundred meters, 100 meters, 50 meters, and then no sediment.
In the middle of the Atlantic, they found a mountain ridge which provided an explanation for the phenomenon.
What Heezen and Tharp discovered was this ridge, the Mid-Atlantic Ridge, actually has a rift in the center of it. So you can see it's this structure here.
A rift ran along the mountain ridge, where new crust was being formed. They had found the mechanism governing Wegener's continental drift.
It's like a horror movie, right? This is crazy. Kids will laugh when they see this. This is the birth canal of the ocean floor. And so there's just this widening crack that every few years gets filled in with lava and then cracks again and gets filled in with lava and cracks again.
So the crust is created in this linear rift, and then it moves out like a conveyor belt away from the axis, with new crust being formed continually.
Today, we know that the Earth's crust consists of a dozen plates moving over a bed of liquid magma. In certain areas, the plates grind against each other. In others, they collide. The continents may also drift away from each other, as is the case of the Mid-Atlantic Ridge, where magma forces its way to the surface and becomes new seabed.
Plate tectonics is the theory that the Earth's surface is divided up into these rigid plates that move with respect to each other. Seafloor spreading is one of the kinds of plate boundaries.
Thorpe and Heezen had found the physical motor which Alfred Wegener had been looking for, the mechanism for moving continents.
In the end, it proved that the theory of continental drift as proposed by Wegener was correct and provided the mechanism which was missing in Wegener's formulation.
Now mankind could watch a 200 million year long film showing how the supercontinent Pangaea broke apart and formed the world as we know it today.
Albert Einstein is without a doubt the most famous figure in the history of science, as well as one of its most innovative thinkers. When his general theory of relativity was published in 1915, there was only a handful of his colleagues who accepted or even understood it.
I mean, it was saying that, in effect, Newton was wrong. So you were going to automatically have a lot of people who weren't going to just accept what Einstein said.
The skeptical scientific elite were eventually convinced of the theory's legitimacy, thanks to a single photo.
With this one picture, Albert Einstein overthrew 300 years of Newtonian physics.
It's absolutely fundamental. This, everybody says, proves the general relativity theory of Albert Einstein.
He was asked to write a popular article for Time. He had become so famous that people wanted to hear in his own words an explanation of the theory of relativity, because it was a very difficult theory to understand.
Einstein's theory even had the greatest physicists of the time scratching their heads.
Well, it was a highly speculative theory at the time. Not everybody agreed, and you have to have training to understand the underpinnings of a complicated theory that had introduced new mathematical tools and new conceptions.
The theory contradicted the Newtonian laws, which had been the accepted scientific norm for hundreds of years.
Well, I think it differed in almost every way. Events in Einsteinian relativity happen in a new concept that is called space-time. And space-time defines the shape of the universe. All objects in the universe travel on lines that we call geodesics, this new concept of Einsteinian relativity.
One of the theory's predictions was that large objects like the sun distort light.
Space itself is like the lens of a glass. The lens of a glass are invisible, but you know the glass is there because light bends when it goes through a glass.
Newton had already concluded that the gravity of celestial bodies influenced its surroundings. But according to Einstein's theory, space-time causes this effect to be much greater.
Einstein was interested in checking this prediction. He wrote a letter to George Ellery Hale, a very famous astronomer. Dear Professor Hale, do you think that the bending of light could be detected during daytime? And Hale, of course, writes back immediately saying, no, we cannot detect this during daytime.
In London, there was a British astronomer who was not merely following Einstein's reasoning. Arthur Eddington also had an idea about how this presumed bending of light could be tested. Eddington planned to use a solar eclipse to find proof supporting Einstein's theory.
So the eclipse of May 29, 1919 was clearly going to be one where you'd have stars that were close to the sun, that were bright enough to be photographed, whose positions were very well known, and you could see whether or not the light was going to be bent.
Arthur Eddington sends his assistant to Brazil, and he himself travels to the island of Príncipe, just off the coast of Africa.
It took them weeks to get there, weeks to get back, weeks to set up, and the path of the eclipse would not be covered with clouds.
The morning of May 29th, the conditions at both locations are far from ideal.
Unfortunately, for Eddington, conditions weren't very good in Príncipe. It was a cloudy day.
During the eclipse, the clouds let up a bit. But when Eddington returns home, he is far from sure whether the costly expedition has really succeeded. Of the nearly 40 photographic plates, practically none of them turned out. But Eddington got lucky.
So finally, they developed the plates from the 4-inch, 10-centimetre telescope from Sobral, and that was the clincher for Eddington.
One of the photos had managed to capture proof of the general theory of relativity.
Eventually, we get to this famous photograph. Here is the bright halo of the sun. And then here you can just about make out these dashes. These are two stars.
In the picture, the sun's powerful corona can be seen behind the passing moon, and off to the side, the light from stars which are in locations they shouldn't be.
Here's another two stars. Here's another two stars. So you know exactly where the Hyades stars should be with respect to other stars on the sky. And you can use the comparison between that previously taken image of the Hyades at night and now the Hyades during the eclipse to see just how much they appear to have been shifted in their position. And that's because the light coming from these stars, coming around the sun, is being bent slightly towards the sun by the gravitational attraction of the sun.
When Eddington measured more closely, he found that the curvature of the light was exactly as great as Einstein's theory predicted.
Those plates showed really excellent agreement with Einstein's theory. He says, well, it's as if space is warped. And so that extra warping of space means that light gets bent twice as much in Einstein's theory as it does in Newton's theory.
Eddington's picture paved the way for a whole new view of physics.
Newton's theory works for everyday events here on Earth. But if you get very strong gravitational fields, the kind of gravitational fields you'd get around a black hole, then you have to use Einstein's general relativity, otherwise you just cannot understand what is going on at all.
And practically overnight, every person on the planet knew Einstein's name.
Einstein became an overnight celebrity, catapulted into the headlines worldwide. When he arrived in New York, he was a superstar.
The famous scientist himself was never worried that Eddington's photos would topple his new theory.
Einstein was so sure that when reporters asked him what happens if this experiment had come out wrong, that Einstein said, well, God must have made a mistake. The theory is correct.
This is Edwin Hubble, one of the foremost astronomers of the 20th century. He's preparing himself for yet another cold night's work up in the mountains over Pasadena.
In 1920, if you were to ask an astronomer, what is the universe? Most astronomers would say it's the Milky Way galaxy. What you see is what there is, period. End of story. That's the universe.
Tonight, he will take a photo which will settle one of the most bitter disputes in the history of science.
It really is a picture that changed the way mankind views the universe.
This was earth-shattering because in this one exposure, the volume of the universe expanded exponentially.
It may be difficult to understand why the city of Los Angeles, with its smog and light pollution, was chosen as the location to build the world's most powerful telescope. But the people who built the Mount Wilson Observatory knew what they were doing.
The steadiness of the atmosphere over the mountain, number of clear days a year, and this site is a very prime site in those regards. So that's why the observatory is sited here at Mount Wilson.
It has been described as one of the great technological achievements of the 20th century.
Building this site was a monumental task, equivalent to the building of the pyramids, I would say. The road that all this material was brought up on was initially just a dirt trail, a dirt hiking trail. Hubble came here because Mount Wilson offered Hubble access to the largest and most powerful telescopes on Earth.
The giant 100-inch telescope was completed in 1917, and shortly thereafter, Edwin Hubble arrived to get to grips with one of the greatest unsolved mysteries of that time. What were the strange clouds of gas spread throughout the celestial canopy? Astronomers called them nebulae, but were in disagreement as to what they were and how far away they were.
So in the 1910s and the 1920s, the debate was whether all these fuzzy things on images that astronomers saw, which they called the spiral nebulae, were actually just small gas clouds within our own Milky Way, or if they were galaxies in and of their own right.
The reason for the dispute was the difficulty of measuring distance in space. Is a star bright because it is close to us? Or is it far away, but very large and distinct?
The whole key in the debate is to measure distances to objects in the universe. The whole key is to know how bright that object is intrinsically.
It became one of the most infected debates in the history of science.
The issue was so contentious that the National Academy of Sciences set up something which we refer to now as the Great Debate.
On one side of the debate is Hollow Shapley. According to him, the stars we see in the night sky, the Milky Way, make up the entire universe, and therefore the nebulae are relatively close to us. Heber Curtis leads the other group, who suspects that our galaxy is not alone, and that the nebulae are in fact their own galaxies, very, very far away from us.
They traveled to the Smithsonian Institute in Washington, D.C. in the year 1920 to debate the pros and cons over the size of the galaxy and the nature of the spiral nebula.
On the night between the 5th and 6th of October, 1923, Hubble takes a photo which settles the debate once and for all.
He would have come in here early, talked to the telescope operator, told him what the agenda was, and then he would have set up his equipment. This is an identical plate to the one Edwin Hubble would have used when he took that famous plate in October of 1923. The photographic emulsion painted on the glass would have been put inside this plate holder here.
Hubble takes aim at the brightest of the mysterious gas clouds in the night sky, M31, better known to us as Andromeda.
When everything was ready, he would open this shutter manually and expose the telescope to the night sky and the object that he was pointing at, which was Andromeda in this case. He would have to stare through a little guiding eyepiece for hours on end until he was done with his exposure, when he would close the shutter back up, take his plate holder down, and develop it.
At first, Hubble doesn't understand the image he has captured.
When Hubble developed this, he saw some stars that had changed in brightness, and he made note of them. And one up in the corner, he marked as a nova.
He first thought it was a novae, but then realized it was one of these stars that we knew the intrinsic brightness of, which is a Cepheid.
Hubble identified one of the stars in Andromeda as a so-called Cepheid variable, a kind of giant star with a known luminosity, which astronomers can use to determine distance between objects in space.
He saw that it had a periodic variation in brightness, and he scratched out nova and he put VAR with an exclamation point. This was the eureka moment when Edwin Hubble had the data to calculate the distance to Andromeda.
And it came out to be millions of light years. So in one stroke, the universe went from 100,000 light years to millions to billions of light years.
Andromeda wasn't a little gas cloud in our galaxy. Rather, it was a separate galaxy of equal size, more than 1 million light years away.
The results were basically so shocking that all the jaws hit the floor.
It settled debate. Hubble sent his result to Shapley, and the people saw it and understood what it meant. Now the galaxy was not special anymore. There were many, many other galaxies just like the Milky Way.
Today, we know that the universe consists of hundreds of billions of galaxies.
It's amazing because back then people couldn't imagine a universe filled with billions of galaxies. That just made people's head hurt.
Hubble's photo gave astronomy a dramatic push. In the years following the discovery, several important breakthroughs were made.
He found that the more distant an object was, the more distant a galaxy was, the faster it was moving away from us. And that implies that the universe is expanding.
Not only this, if you run the videotape backwards, it's like running a videotape of an explosion backwards.
Catholic priest and cosmologist Georges Lemaitre was the first to theorize that if all galaxies are moving away from each other, it must mean that at some time in history, they all derived from a single point, something which would later be called the Big Bang.
This is where the journey ends. It is approximately this far away, and as far back in time, 13.2 billion years, that we can see for the moment, a cosmic moment from the dramatic birth of the universe. Instruments of the future will probably be able to look even deeper into time and space.
The next big revolution will be led by gravity wave detectors. Detectors that can measure vibrations from the instant of creation itself.
If man succeeds in capturing an image of the moment of creation, it will have a very special place in the great photo album of the history of science.
In the next episode, we travel inwards.
It's like a photograph, but 500 years old.
The human body is opened.
Everything is absolutely correct.
It's one of the most important photographs ever taken.
The secrets of life are revealed.
They couldn't have built their model if they hadn't got Structure 51.
And the journey ends in the paradoxical world of the atom.
I started writing the M over here, and then I made a mistake. I'm trying to move this atom, and the atom won't move. And after a while, you develop a sort of personal relationship with that very stubborn atom that will not move.
Everything captured on film.